we said that it looks complicated. There's a trick, and I'm going to talk about the trick right now and write follow the solution in another page. So what are we going to do is we're going to write down all equations to find out the difference in terminal temperatures. In terms of flux, which is constant throughout the system. Okay, so that's the trick. Now, I want you to be aware of the fact that we already derived the temperature profiles. We know them, but in terms of the T0 and T0 and T2 instead of TF1 and TF2, and we haven't figured out the flux. Sorry, we haven't found out the flux, the amount of flux in terms of TF1 and TF2. So we're going to do two things. We're going to find out the fluxes, and then we're going to find out the temperature profiles using those fluxes. Okay. Okay. Let's do the trick described on the previous page. Okay. So for material one, so basically, let me first show you the following, what I mean, basically. So you have these regions, right? You have this TF1, you have this TF2, correct? And imagine that you have this temperature here, you have this temperature here, you have this temperature here, maybe you have this temperature here, and you have this temperature here. So there's just like a change in the temperatures, different regions. This is T0, T1. And T2. And I'm going to write down the following. I'm going to write down an equation for TF1 minus T0 first. And then I'm going to write down an equation for T0 minus T1. And then for T1 minus T0, sorry, T1 minus T2 within this region. And then for the T2 minus TF2. And then if I know those expressions, I can add this, and this, and I can find out the difference between the TF1 and TF2 in terms of the fluxes, which is constant throughout the system. And then one can actually, yeah, so that you can actually find out the relation between the temperature difference, the difference of the fluid temperatures and the fluxes. Okay, so that's the recipe that we're gonna do. So let's start with the material one for material one. We know that minus K1 dt1 over dx is equal to Q0, which is constant, right? how do we know that the Q0 is constant? Because it came out to be so in the shell balance, right? If you remember. And from here, if you actually rearrange this, dt1 is equal to minus Q0 over K1 dx. And if you take the integral from T0 to T1, okay, where x varies from 0 to L1. And you find the following: T1, T0, or yeah, you can write it in the other way around if you like. So let's make this plus, let's make this minus. So this is going to be T0 minus T1 is equal to Q0 over K1 times L1 minus 0, which is L1. Okay. Let's call this equation 1. Okay. Now for material 2, similarly, for material 2, we're going to have the same equation actually, but it's going to be not T0 minus T1, but it's going to be between T1 and T2. So T1 minus T2 is equal to the same Q0, because basically you know that at the interface, the Q0 of the material 1 is the same as the Q0 of the material 2. So basically you're talking about the same Q0s divided by, but this time K2, be careful. This is for material 1, this is for material 2, okay? And then instead of L1, the thickness of the first material, it's going to be L2 minus L, sorry, it's going to be L2, I'm sorry, it has a thickness of L2, right? It's basically the L1 plus L2 minus L1, which is L2. So let's call this equation equation number 2. Okay. And let's write the Newton's law of cooling for this side. Okay. And you find Tf1 minus T0 times H is equal to the Q0, but you can write it as Q0 over H1 for the fluid 1. So let's call this equation 3. And for the other side of the material, for fluid 2, this was for fluid 1. Now this is for fluid 2. T2 minus Tf2 is equal to Q0 again divided by H2. The reason why we have the Q0 again the same, because the Q0 is the same throughout your system, because whatever is actually whatever heat is flowing in this region, you have the same heat flux here. You have the same heat flux, you have the same heat flux. Heat flux is the same because the amount of heat must be the same, because that's whatever comes in should come out. And also this has a constant area, so the area is not changing throughout the system. It's a slab geometry, that's why. Okay, but you can also use the boundary condition at each case. For example, at this boundary, the flux due to Newton's law of cooling must be the flux due to the Fourier's law. Okay, so that's equation 4. So let's write them side by side. Okay. T0 minus T1 is Q0 over K1. Any questions so far, by the way? TF1 minus T0 is equal to Q0 over H1, T2 minus TF2 equal to Q0 over H2. Now, here is the thing. I can simplify this equation if I actually add them up and if I have the correct rearrangements, okay? So make sure you have the correct rearrangements, and when you have it, it's gonna be simplified as follows. T1s are gonna cancel, minus T1 plus T1, plus T2 minus T2 are gonna cancel. Plus T0 minus T0 are gonna cancel. So you have this nice difference between TF1 and TF2 is nothing but the sum of all these terms, which is basically Q0, right? Times L1 over K1 plus L2 over K2 plus 1 over H1 plus 1 over H2. What a beautiful formula is this, right? So actually it derived the relation between the temperature differences and the flux. And you can actually solve for the flux. That's what we wanted, right? The flux, Q0, comes out to be equal to TF1 minus TF2 in the numerator divided by L1 over K1 plus L2 over K2 plus 1 over H1 plus 1 over H2. Any questions so far? Okay, so there's something new that we actually learned here. Here's the thing. This equation looks like our Newton's law of cooling, right? In Newton's law of cooling, resembles Q0 is equal to TF1 minus T0 divided by 1 over H, right? I just make it look like this above formula, correct? And or maybe you can write it as H times this, or H1 times this. But here, instead of H1, you have this 1 over this term, okay? But it looks like the heat transfer coefficient. So we call it basically overall heat transfer coefficient. So we say Q0 is equal to U times TF1 minus TF2. And this U is called the overall heat transfer coefficient. Okay, the reason why we call it heat transfer coefficient because it looks like this H1 here, and the reason why we call it overall is because instead of TF1 minus T0, we have the overall differences, the difference between the temperatures at the two very opposite ends, the two fluid temperatures. Okay, so okay, and another nice thing about this, basically, so you can write this U as 1 over L1 over K1 plus L2 over K2, right? Plus 1 over H1 plus 1 over H2. Right? And you can also write it as 1 over U is equal to 1 over L1, sorry. It's equal to 1 over, yep. I guess it's better if we just keep it there. Yeah, let's not write it as 1 over U. Okay, it's kind of, it might be confusing. Okay, so what is the nice thing about this equation? So, nice thing about this is that you can write so let's say you can use it easily for different number of layers. Meaning that in this case you had a composite material which had 2 different types of materials. You can have scenarios where you have 3 composite layers attached to each other. You can use this formula pretty easily. So here's the schematics how you can use. So for example, imagine that you have T0 here. You don't have any fluid on the left. Imagine that you have a material with K1 with a thickness L1, another material K2 with a thickness L2, another material K3 with a thickness L3, another material K4 with a thickness L4. And imagine that you have a fluid here with a heat transfer coefficient H and with a temperature Tf, right? So you can write down your equation, flux is equal to U, the overall heat transfer coefficient, times Tf minus T0, the temperatures at the 2 very opposite ends. And you can write the U in terms of the K1H, K2, L1, L2, all those constants. And if you have a look at this function, this formula, you're going to see that it should be 1 over, right, L1 over K1 plus L2 over K2 plus L3 over K3 plus L4 over K4 plus, and the heat transfer resistance due to this fluid contact, you have 1 over H. Okay. So very easy and straightforward methodology, right? So you don't need to write down these again and again, but you just can use the concept of overall heat transfer coefficient to write the flux as to relate the flux to the temperature difference at 2 very opposite ends. Okay. Any questions so far? And these equation also looks like the equations in the equations you learn in physics classes, I guess. It's the Ohm's law, right? The additivity of the resistances. Well, basically, it's the same thing. You're adding the resistances here. In this case, we have the flux is equal to the difference in the temperature delta T, which is the driving force for the heat to move from one place to another, divided by resistances. And here the 1 over U correspond to resistances, and you can actually think about it as the resistances. You can add the resistances. For example, you can just add 1 over H, K1 over L1, and so on. Sorry, L1 over K. You can add those resistances, and it's going to give you the overall resistance. So these, each of them is just one resistance which can be added to the denominator. Any questions so far? So let me just write it for your convenience here. This is analogous to flow of electricity, or Ohm's law. I is equal to delta V over R. In Ohm's law, delta V, the voltage difference, is the driving force for the current to move. I is your flux in that case, and so on.